Hello class. Where we ended last time was calculating the Q for a reaction that was under non-standard conditions. So to review what that looked like, we had a reaction, standard cell notation, of aluminum being oxidized to aluminum 3 plus with a molarity of 0.15 in solution, and a copper 2 plus molarity in solution of 0.025 being reduced to copper 0. So the fact that these are not one molarity indicates that this is under non-standard conditions. And we calculated the Q by first determining the net reaction, which was 2 equivalents of aluminum solid reacting with 3 equivalents of copper ion to make two equivalents of aluminum ion and 3 equivalents of copper solid. Only the aluminum and the copper were in solution, so our Q is going to be equal to those values raised to their coefficients divided by one another, which gave us a Q that is equal to 1,440. So now we need to figure out whether or not the reaction is spontaneous under these conditions. So normally in the past what we might have done is use this equation here. Delta G is equal to delta G naught plus RT ln Q. But in this situation, delta G is unknown. It's not given to us in the problem. We could use standard values from an appendix in order to calculate this, but we currently don't have it. But what we can use is delta G being equal to negative NFE cell for both of these delta Gs. So negative NFE cell, not standard, is equal to negative NFE cell standard plus RT ln Q. We divide both sides by negative NF and we get E cell is equal to E cell naught minus RT over NF times the natural log of Q, and we bring in all of these values. So we have our E cell from the last page is equal to positive 1.999 volts, and our gas constant, temperature, number of electrons being transferred, which is 6 when balanced, and Faraday's constant. And then we have the natural log of Q, which is 1,440. When we do all this math out, we get an E cell that's equal to 1.999 volts minus 0.03 volts, and we get an E cell that's equal to positive 1.97 volts. As we discussed previously, when you have a positive E cell, that always gives you a negative delta G. So this is an E cell that tells us that the forward reaction is indeed spontaneous. In the next set of notes, we're going to look at reactivity and predicting reactions in 3 different ways, and we're going to stop before the pH dependence of reduction potential. So, first, in example 9, the following 2 half reactions correspond to 2 half cells that are combined to form an electrochemical cell. And all we have are the reactions, and what we don't have are the reduction potentials. Remember, when we're dealing with any reaction, how well something gains or loses electrons is always written as a reduction because they're corresponding reduction potentials. So we have plus electrons on both sides. So on page 117, so a few pages away, we have a whole table full of reduction potentials. And in this reaction, we have manganese oxide being reduced by 5 electrons in the presence of 8 protons to form manganese 2 plus in water, and that has a reduction potential of 1.51 volts. The other reaction is iron 3 plus being reduced by 1 electron to form iron 2 plus. Recall that, or not recall, but notice in this table there are a few different iron compounds, so you have to be careful to make sure that you're using the correct iron. This was iron 3 plus reduced to iron 2 plus, and that's positive 0.77 volts. So we have positive 0.77 and 1.51 volts. So when we consider these reactions, we have iron 3 plus being reduced to iron 2 plus, and that reaction has the more negative reduction potential. Both of these reduction potentials are positive values, but the iron reaction is less positive, but in terms of reduction potentials, I like to call that more negative, because a more negative reduction potential means that it is more difficult to reduce. And the manganese oxide being reacted to form manganese 2 plus is less negative. It's a more positive value. The more positive value means that it is easier to reduce, so the easier to reduce reaction should be our reduction reaction, which is our cathode. By deduction, we can then figure out that the more difficult reaction to reduce would rather oxidize, which would then be our anode. So in order to write the overall cell reaction, we have to combine our reduction reaction and our oxidation reaction. Both of these are written in terms of reductions so that we can use the reduction potentials, but when we combine them, we have to flip the oxidation to be more reminiscent of what's happening in reality. The reality is that this is an oxidation, so we have to go from iron 2 plus to iron 3 plus and losing electrons. So what does that look like? When we take the reduction reaction, we can take this manganese reaction and just bring it right down here. no change at all. Manganese oxide plus 8 protons plus 5 electrons gives you manganese 2 plus and 4 waters. That's our cathode. Iron 3 plus reacting to form iron 2 plus needs to be our oxidation. It's currently written as a reduction, so we have to flip that to make it an oxidation. And when that happens, we get iron 2 plus gets oxidized to form iron 3 plus and releases 1 electron. In order to get a balanced net transfer of electrons, we have to multiply by 5 for our iron reaction. So what we really have is 5 iron 2 pluses react to form 5 iron 3 pluses, and 5 electrons are produced in the oxidation. So when we combine our reactants, we have manganese oxide reacts with 8 protons and 5 equivalents of iron 2 plus to form our products, manganese 2 plus, 4 waters, and 5 iron 3 pluses. So that is our overall chemical reaction. We do not include our electrons because they're equal on both sides of the reaction arrow, so they cancel one another out. For our E cell, that's going to be equal to cathode minus anode. We've already discovered that our cathode is our manganese reaction, and our manganese reaction has a reduction potential of 1.51 volts. Our anode is our iron reaction, so it's positive 0.77. So we get 1.51 minus 0.77, and we get an E cell that's equal to positive 0.74. That's a positive value, which means that it will be spontaneous and have a negative delta G in the forward reaction, which means that we've put together these reactions correctly to make a spontaneous reaction. Check. Example 10 is what is a little bit more normal for the a research scenario where you're trying to see what happens when you combine two things and what reaction would happen. So here we're going to take a look at the following half cells when they are combined. The reaction of zinc 2 plus to form zinc solid, and the reaction of silver plus 1 to form silver solid. So we need to go back to our table on page 117, and we're going to look at zinc 2 plus being reduced by 2 electrons to form zinc solid, which has a reduction potential of negative 0.76. And we're going to look at silver plus being reduced by 1 electron to form silver solid, positive 0.80 volts. So when we record those values, we don't actually know which one is which, the anode versus the cathode. We could use our logic like we did last time in order to figure out which one might be the correct one and then test to make sure it's a spontaneous reaction. But we could do the opposite way first and just do 2 quick tests and figure out which combination gives us a spontaneous reaction. So first, if we set the negative 0.76 equal to our cathode, we do negative 0.76 minus 0.80, and we get negative 1.56 volts. Incorrect. That is not a spontaneous reaction. So that must not be the cathode value, and that must not be the anode value. So we switch them, and we get positive 0.80 volts minus negative 0.76. They're looking good since we're subtracting a negative value, and we get a positive 1.56 volts. That's spontaneous. In this order, we have 0.80 volts is our cathode, which corresponds to our silver reaction, so that must be our reduction, which means that our zinc reaction must be our oxidation. So if we were to combine these reactions to form the overall chemical reaction, we would have to flip the zinc reaction because it's the anode, and we have to flip it to show that it's an oxidation when we write the overall chemical reaction. Finally, we're going to take a look at a more challenging example to show how much information is actually necessary to solve one of these problems. So first, we're going to look at a cell that's 2 equivalents of sulfate react with iodide to form sulfurous oxide and 2 equivalents of iodine. And we're going to write down the 2 half cells to determine the overall E cell. And we don't know which one of these is the oxidation, which was the reduction. So we go to page 117, and we find that our sulfur oxidation reduction potential is positive 2.01 volts, and our iodine reduction potential is positive 0.54 volts. So we record those values here, and we get the sulfur reaction has a reduction potential of 2.01 volts, and the iodine reaction has a reduction potential of 0.54 volts. But what we're looking at is, in this chemical reaction, which thing is being oxidized and which thing is being reduced. This is purposefully written with one compound that would take a little bit of time to figure out what the oxidation states are for everything in the compound. But what we do have is very simply iodine being reduced because we have iodine in the elemental form as a 0 oxidation state as a reactant and a -1 oxidation state in the product. This gives us everything we need. So iodine is being reduced. That means that the sulfur reaction must be being oxidized. So in the reaction as written, our 0.54 volts is our reduction, which is our cathode, and the sulfur reaction 2.01 volts is therefore the oxidation and must be the anode. So when we write the E cell for this reaction, it's cathode minus anode. So we have 0.54 volts minus 2.01 volts, and we get an E cell that's equal to negative 1.47. So if the question is, if we put sulfate and iodine together, will this forward reaction happen? Well, the answer is no, because we get a negative E cell, which would correspond to a positive delta G, which tells us that the forward reaction, as written, is non-spontaneous. So this happens very frequently in research, where you are trying to tell if a certain redox reaction with two things would react together spontaneously. In this situation, they absolutely would not. And we're going to end there, and we will not be getting to the pH dependence of reduction potential.